A relation is any set of ordered pairs. So relation sounds like relationship. An ordered pair has an x and a y. Those x and y variables have a relationship together. So almost a lot of things in math are relations. Things are related. I'm using that word a lot, aren't I? That's STEM. A more specific kind of relation is called a function. This is the definition I'm not going to spend a ton of time with because we have killed and drilled this since middle school algebra 1. Alright, so a function is a relation in which every input, the x's are the inputs, corresponds with exactly one output, or y. Right, so every x matches with one y value for a function. Now, what test did we use to determine if a graph was a function? Vertical line test, all right? So we've done the vertical line test. We'll look at it briefly within something else in a few minutes. But if a graph passes the vertical line test, it's a function. All right, nothing new in those first two definitions. Now, this is a new characteristic of a function. There's a special kind of function that can be called 1 to 1. Right? And there's technically little hyphens there. You don't have to put the hyphens if you don't want to. But a 1-to-1 function is a specific kind of function. Now, it gives you this really mathy looking definition right. It says x sub 1 is not equal to x sub 2, then f of x sub 1 is not equal to f of x sub 2. And I know when I was in high school before, I did a lot more math. When I saw this, I usually skipped those problems or skipped looking at it because I didn't know what it means and it just looked complicated, right? Is that about right? Like, I don't know, some of them not look at it. What that means is that every input, different inputs, right? So different x values give different y values. So no y value is going to repeat. Okay? So every different x value gives you different outputs. So if my function, if I have an x value of 2, and I put it into the function and I get an output of 5, no other x value gives me an output of 5. 5 is only used once. Okay? And we'll look at that in just a second. The next part says you can be a 1-to-1 function only if you're actually a function first. So you can't be 1-to-1 without first being a function. They go together. And similar to the vertical line test, there's a test to tell if a graph is a function, or 1-to-1. It's called the horizontal line test. So we're going to look at that in just a second. But the vertical line test tells you if you're a function. The horizontal line test tells you if you're a 1-to-1 function. Okay? So let's look at the bottom. We have some tables here to start. Of the 4 tables below, one of them is a 1-to-1 function. So let's determine which one it is. All right, so let's look at the first one. In order to be 1-to-1, you have to be a function. Is number 1 a function? No, why not? Yeah, see these two, like these x's of 4 here give me different outputs. That breaks the definition. Same with the y of, or the x of 9, 2 different outputs. So this is not 1-to-1 because it's not a function. So it can't be 1-to-1. What about number 2? Is number 2 a function? Yes. Is it 1-to-1? Look at the y values. No, why not? Because the y value of 1 repeats itself. So it is a function, but it's not 1-to-1. Okay. So you can be a function without being 1-to-1. All right, look at number 3. Is it a function? Yes. Is it 1-to-1? Yes, none of these y values repeat. So this table does represent a 1-to-1 function. Every x is different and every y is different. All right, and then number 4, is it a function? No, what x breaks the rule? -2. Okay, so this one is not a function because the x's of -2 have different outputs. Okay? Okay with the table? Now the graph is even easier. The following here, of the graphs, which ones of those graphs are functions? So use the vertical line test. Shout them out.
1 and 4.
1 and 4. They both pass, 1 and 4 both pass the vertical line test. 3 and 2 fail the vertical line test. They're not functions. So they can't be 1-to-1. Now use the horizontal line test. Which of these graphs, 1 or 4, would pass the horizontal line test? 4. So 4 here is 1 to 1. Okay. Pass. Got it? Easy definition to start. All right, one new thing down for the day. Flip your page over. That's one thing that a function can be. A function can be 1 to 1. A function can also have another distinction. It could be called even, odd, not add, I wrote add, odd, or neither one or the other. Okay? So not every function is going to be even or odd, but some of them will be. So let's talk about what that means. Let's do even functions first. Even functions, there are 3 ways to tell if a function is even or odd. If I ever ask you, which I will, is this function even or odd, you can use any one of these methods, okay? I don't care which one as long as you know how they all work together. Now, even functions have graphs that are symmetric about the y-axis, okay? So if I look at this picture, I'll flip back and forth between the rules and the function. If I look at this picture, I see that this parabola reflects over that y-axis. It's symmetric. So that's why that one's an even graph for the picture. Now, even functions also tend to have equations with all even exponents. Sorry, it froze on me there, but we'll still talk through it while it's deciding to write. So we have all even exponents. And when I look at this equation, this is the equation of the graph that's made here. If I look at those exponents, I'm just going to write so that the numbers will come out. There we go. When I look here, notice that 2 is an even exponent. And then actually, this is a tricky one. The constant here technically is x to the what power? 0. 0 is considered an even number. So here I have 2 even exponents, which follows the rule, but I have all even exponents. Okay? And then the last one. This is the old way of doing it. When I was in high school, we had to do this. It was called, we're really going to do a proof here. I know, I say proof and you're like internally grown. Oh man, I have to do proof. Not a two-column proof. It's called an algebraic proof. Now the way this works is, the rule says if I take f of negative x, that means if I put negative x in for x in this function. So I want everyone to write this down. I'm not going to ask you to do this a lot. I want you to write it down so you see how it works. If I take negative 3 and then put negative x in, and then plus 4. I'm going to simplify that expression, all right? I've inputted negative x for the input, or put it in the input. What is negative x squared? Yeah, just x, right? A negative, when you square it, turns positive. So this simplifies to be negative 3 and then positive x squared plus 4. Well, what do you notice about this equation and the original equation? They're the same. If I put negative x into the equation and get the exact same equation out, that means it's an even function. That was a proof right there. Those 2 lines. So an algebraic proof. There's more to proofs than just 2-column proofs. Right? So if you ever decide to be a math teacher or a math major, applied math, engineering, you're going to do a lot of proofs. Right? I did college and grad school. I did proofs all day long, and I never did a 2-column proof ever again. So there's a lot more to it than that. Okay, does that make sense? All right, I think, which rules do you think are the easiest to remember? 1 and 2, right? And that's fine, that's all you really need to know, right? Knowing the third one's nice, but if you could look at the equation and the graph, then you're probably good to go. All right? Odd functions. Odd functions have graphs that are symmetric about the origin. Okay? So your origin is the point 0, 0. One way I kind of think about symmetric about the origin is that the graph, like opposite quadrants, look the same but reflected. So like the first and third quadrants look the same. 2 and 4 look the same but upside down. Okay? So that graph is reflected over the origin. You did some of those reflections last year in geometry. Odd functions have equations with all odd exponents. All even for even, all odd for odd. So if I looked at the equation here, it's easy to see that the exponent of 3 and the exponent of 1 are both odd numbers. So it's an odd function. And then let's do one more proof for today. If I was trying to evaluate f of negative x, I'm going to take negative x and input it for the value of x. So 2 negative x cubed minus 4 times negative x. What's a negative number cubed? Positive or negative? It's a negative. So I'll have positive 2 times negative x cubed, which becomes negative 2x cubed. Right? That negative, I just pulled it in front because of the commutative property. And what's negative 4 times negative x? Positive 4x. What do you notice about this equation and the original? The signs are all opposite. Every sign changed. The 2 became negative, the negative 4 became positive. That's what happens in an odd function. If you put negative x into the function as the input, all the signs will change. Good? All right, one more. You can be even, you can be odd, or you can be neither. You can just be a function. So, not even or odd, neither functions are not symmetric. So here you can see my graph isn't symmetric over the y-axis. It's not symmetric over the origin. The exponents are all different. They're not all even or all odd. So here I have an odd to start, 3, the minus 3x squared. That's even. Since there's sum of both, we're not even or odd, right? Remember the 4 has x to the 0 on it. So that's why the equation is not even or odd. And then if I put negative x in, I don't get the same equation. I also don't get an opposite equation. And I won't go through the proof of it again. But what would happen is the odd exponents, when I put negative in, those signs would change. That negative 2 would become negative. The even one would stay the same. So some would change, some would stay the same. That's neither even nor odd. Okay? Good? New fact number 2 of the day. Not too hard? No? Have you done even or odd before? No? You didn't even know equations could be even or odd. You thought that was just numbers. So equations can be even or odd. Now, we're going to talk about parent functions. This is the key part of the lesson today. When you get to pre-calculus next year, there's going to be a list of like, I want to say 15 or 16 parent functions they're going to make you memorize. It's going to be the first thing that you do when you get to pre-calc. There'll be some of these plus like 7 or 8 more. And they're going to make you graph them and recognize them by sight, and then also move them, left, right, up, down, reflections. We'll do that this year, just not with all of these functions, okay? So I carved down what pre-calc does, and I chose 8 functions. 8 functions that you're going to see this school year. Of those 8, 6 of them are ones that I'm going to test you over. Okay? 2 of them I'm not going to ask you because they're totally new. Well, one of them's totally new to you this year. But I'm just not going to test you over those until later in the year. Okay? So from these, we're going to use our calculators if we need to. We're going to graph the function. You're going to need to know the graph of the function without a calculator. So you'll have to plot points. And like graph it accurately, and then you'll have to decide if it's even, odd, or neither. Okay? Then there'll also be like a match. Like you might have to match it. If I give you the graph, you have to tell me what function it is. Okay? All right, it won't be that bad. Especially because the first one you should know. It's called the identity function. F of x equals x. That's just like the equation y equals x. You all should know how to graph that. So you can use your calculator, but I think we can do points without our calculator. I'm going to say some key points here. Negative 2, negative 1, 0, 1, 2. If I put negative 2 in for x in this function, what output do I get? Got it. If I put negative 1 in, what do I get? That's why we call it identity. It's the same. 0 gives me 0, 1 yields 1, 2 yields 2. Right? This one's an easy one. You've graphed this a ton when you were in geometry, y equals x. All right? So I plot the points negative 2, negative 2, negative 1, negative 1. And you'll know that this is the line that goes through the origin with a slope of 1. So once you plot your key points, you'll know what it looks like. You did a lot. We're going to do more with this one this year. In geometry, you spent time with this when you were reflecting. like quadrilaterals and triangles and stuff. General description of this graph. I would say it's a line with a slope of 1 through the origin. These are very informal descriptions, but some way that might help you remember what the graph looks like. Now, when I look at that graph, would you say that that identity function is even, odd, or neither? What do you think, Charlie?
Odd.
Odd. Yep, why do you say it's odd?
Because its exponents are odd.
Yeah, x to the first. 1 is an odd number. That's an odd function. It is also reflecting over the origin. Is that graph 1 to 1? Yes. It passes the horizontal line test, so it is a 1-to-1 function. Okay? Parent function number 1. Oh, I guess I didn't even tell you what a parent function was. Parent function is the most basic function of any family of functions. It's like mom, dad. It's like a mother function. So a family of functions would be the lines, right? You can have lots of different lines that look different. That's the most basic line. The next one is the square functions, parabolas. You can have lots of parabolas. Wide parabolas, skinny parabolas, long, short ones. So this is the most basic parabola, okay? And this is f of x is x squared. So let's pick some points. We'll still do the same -2, -1, 0, 1, and 2. Now, you should probably know how to graph this. We're going to spend so much time with this function later this year without our calculators that you better know how to graph this parent function at some point. So might as well start now. What is -2 squared by squared? 4. -1 squared, 1, and then 0 squared is 0, 1 and 4. Okay. So we plot the points. We have -2, +4, -1, 1. You know what a parabola looks like. And I'm even going to plot 3, 9, and -3, 9 just to fill out the grid and connect my points. So I have a parabola. I would say the description of this trend is a parabola that opens up. So it's a parabola that opens up. Its vertex is at the origin. Would you say that that parabola is even, odd, or neither one? Even. Why is it even? It reflects over what axis? The y-axis, and its exponent is even, 2. Is that 1 to 1? No. Good? Good there? All right, so we know lines, we know parabolas. Let's look at a cubic function. So you've probably seen a cubic function before. X cubed. All right, so same points here. We're going to start with -2, -1, 0, 1, 2. So when I put -2 into the function and make -2 cubed, what is -2 cubed? -8. When I cube any negative to an odd power stays odd. What's -1 cubed? -1. 0 cubed? 0. 1 cubed is 1, and 2 cubed is 8. Alright, so when I graph this, I'll have -2, -8. Have those points here. And if you've never seen this graph before, it's kind of a cool graph. We'll spend more time with this in the spring. The graph comes up, it kind of squiggles and flattens out, and then goes back up. So it's kind of a cool looking graph. It's a little different. So how would we describe it? I would say it's increasing, and then I would say maybe it flattens out around the origin just a little bit. So that's a cool graph. We can graph x cubed, cubic function. Is that cubic function even, odd, or neither? Odd, yes, that is 1. The exponent is odd, 3. You can also tell because it's symmetric. The first and the third quadrants look the same. Is that graph 1 to 1?
Yep.
Yep, good. All right, now the next one's kind of cool. If you haven't done this one yet, I will expect you to be able to recognize it in a graphic because it's not hard. But we're going to spend more time with quartic functions later. Quartic, the stem quart, means 4. So x to the 4th. Let's pick the same key points we've been picking here. So let's start with negative 2. And what is negative 2 to the 4th power? 16. It turns positive, and 2 to the 4th is 16. What's negative 1 to the 4th? 1. 0 to the 4th is 0. And then we're symmetric. So 1 to the 4th is 1. 2 to the 4th is 16. Now, obviously, we don't have enough room on here to plot 2 to the 16, or negative 2 to the 16. So we'll skip that point. We'll have negative 1, 1, because that point would be way up off the board here. 0, 0, 1, 1. Now, before you connect those, I want to show you something. I'm going to pull up Desmos here. Now, the first graph that I put up there, that is x squared. All right, that is our square function. We've graphed that one for a long time. This next one is x to the 4th, the black graph there. Do you notice a difference between those? What would you say is the difference about that second graph? What? Yeah, the bottom. See how much flatter the bottom is? So it has those same points, 1, 1, and negative 1, 1. But notice at the bottom, x to the 4th is flatter. Right? That's a characteristic of a quartic parent function. All right, so when you graph this on your paper, maybe try, I know that it comes up really narrow here, but maybe try to draw a graph that looks like it has a little flatter of a bottom. All right, it's really narrow because 2 to the 16th is a lot bigger. It grows faster than like x squared, but it has a flat bottom. All right, so when we do a description, we'll say it looks like a parabola with a flat bottom. Just a little bit different. And actually, just for fun to show you, if you were to graph x to the 6th, that red graph, see how it even gets flatter than x to the 4th? So as your power goes up, the base of that parabola gets flatter and flatter. All right. So let's see. Let's go back here. Is that an even or odd function? Even. Okay. 1 to 1? No, because it fails the horizontal line test. All right. Are we good with those? Those are kind of like our regular power functions. X to the 1st, x to the 2nd, 3rd, and 4th. This next one, I don't know. Some of you have seen it. Some of you might not have. The absolute value function. What's the absolute value of a number? Yes, it's distance from 0. So remember, when I took the absolute value of any number, what was the answer? It was always the positive version of it. All right, so that's going to help us. Let's do our key points here. Why don't we do same points, negative 2. We'll change this up eventually, but for now they work. If I take the absolute value of negative 2, what do I get? Positive 2. Absolute value of negative 1 is 1, 0, 1, and 2. Now, just for your reference, you can graph absolute value on your calculator. If you have a TI Inspire, I'll show you later. But if you're on the TI 84, if you wanted to graph, you would go to Math, over to Number, so arrow over, and it's the first one. It says ABS, absolute value. Then you would click Enter, and then you could just type in the X. Okay? And then you'll see that's what the absolute value function looks like. It looks like a big capital V. Okay? So that's what it looks like. Let's graph that on our paper. If you have an Inspire, I can show you. It's really easy to do. But now, the reason the graph looks like the letter V is because when you take the absolute value of a number, you have to get the positive version. So it basically just took that linear function, our original function that we started with, the identity here, right? And it took this bottom part and it flipped it up into the positives because those outputs have to be positive. Does that make sense why that happened? All right, so there's our absolute value function. I would say it looks like a V. like the letter V. Is that even, odd, or neither? Is it symmetric over the y-axis or the origin? Y-axis, so that would be an even graph, which is a little different because you can't really tell from the equation there, so you have to know the graphical. And then is that 1 to 1? No. Okay. Have you seen the absolute value function before? No. All right, we're going to spend a little time with it in a couple weeks, actually. So there's your absolute value function. All right, something else, you've seen this one, the square root function, square root of x. We are going to spend a lot of time with square root of x in probably like March. February or March. Let's see. So if I take the square root, here's the key points I'm going to use this time. -1, 0, 1, 4, and 9. See, I changed it up on you finally. So let's start with the square root. If I put -1 under the square root, what do I get? Nothing. I will tell you how to take the square root of -1 eventually, but today's not that day. So if you put that in your calculator, you will get an error. All right, I just wanted to remind you that you cannot take square roots of a negative right now. You'll get there eventually, but not now. What's the square root of 0? 0. Okay, what's the square root of 1? Square root of 4? And square root of 9? 3. All right. So when I plot that, I start at 0, 0, 1, 1, 4, 2, 9, 3. And that's actually the same pattern as the square function, the parent function for that parabola, x squared, only half of it and tipped on its side. Okay, so this is an increasing function, and it looks like half of a sideways parabola. Again, very formal definition here. I just want to give you something that'll help you remember. Okay, so it's half of a sideways parabola. Is that function even, odd, or neither? Neither. Yeah, it's not symmetric over the y-axis because there's nothing on the other side, and it's not symmetric over the origin because there's nothing in quadrant 3. So that would be neither. Is it 1 to 1? Yes. Okay. So those are the 6 functions that I'm really going to test you over, right? You should be able to identify them by their picture and graph them. If I give you the function, you should be able to plot points and graph it. The next 2, I want you to be able to recognize them by sight. So look at the picture and tell me what it is, but I'm not going to make you graph them, okay? The first is the exponential function. Now, I typed it wrong on your paper. Your paper says e to the x. You're going to learn e to the x, I don't know, in a couple months. I'm not doing that one right now. I meant to say 10 to the x, so can you scratch that off? Similar function, but we're going to get to that later. You don't know what e is yet. So 10 to the x. And here are the key points I wanted to do. Oh, I remember. -2, -1, 0, 1, and 2. Maybe I want to do -3. It's okay. All right, let's type this one into our calculator. We'll make sure. So we'll go to y equals. We'll type 10 caret to get x in the exponent. And you know what an exponential function looks like. You did exponential functions in Algebra 1. We're going to spend a lot of time with exponential functions in our class. Let's go to the table so that we can fill in the values. So it looks like -2 is at 0.01. So it'll be our first guy. -1 is at 0.1. 0 was 1. 10, and then 100. And I know 100 won't fit on there. Now, when I graph this, so -1.01 is really close to the axis. Just do your best. 0, 1, 1, 10. And then you saw, looking at the table, that these y values just got smaller, 0.001, 0.0001. So they got really, really close to the axis here. But as I look at the table, let me connect those. As I look at the table, I know you have scientific notation, but does this graph ever actually hit the x-axis? No, do you know what that's called? It's like my favorite math word. It's called an asymptote, all right? So this graph has, I'll spell it for you, and it's spelled funny, A-S-Y-M-P-T-O-T-E, asymptote. Sounds like a silent P. It's a really cool word. It means it's a line you approach, get really, really, really close to, infinitely close, but you never actually touch it. So this graph has an asymptote at the line y equals 0. That's the x-axis. It gets really close to the y-axis. It's never going to touch it. Okay. Now, is that exponential function even, odd, or neither? Neither, right? It's not symmetric. And is it 1 to 1? Yes. Okay, so we've at least seen 10 to the x before. This next graph you've probably not seen. One more. It's called a logarithmic function. Log of x. We will learn what a logarithm is in a little while. Well, not like today, a little while, but a couple weeks, a couple months, a couple weeks, a little while. All right, so a logarithmic graph. I would like to plot 0. No. Yes, sorry. 1, 2, 3, and 4. All right. No, I lied. I'm sorry. Erase those. I'm trying to do this by memory. 0, 0.01, 0.1, there we go, 1 and 2. I got it now. And lunch, I forgot over lunch. Let's plug this in our calculator. So y equals, we're going to graph log is on the left here, says the word log, and then x. Now, the graph on your calculator is a little bit misleading here. This graph actually also has an asymptote. It comes down. It just didn't graph it for you. But the asymptote here is on the y-axis. So if I look at the table, I can't get all those points I wanted, but I can get some of them. So 0, what happens at 0? It says error. So actually, you can't take the log of 0. We'll talk about why when we get to logarithms in like a month or so. But for now, we don't know why. I'll skip these. We'll come back to them in a second. What was log of 1? 0. And then, sorry, I changed, not 2. I meant, I got it now. I wanted 10. Sorry. If you had me 8th period, I would have had it together because I would have just done this class. So log of 10. Can you scroll through your calculator? What's log of 10? 1. All right. Now, really quick, let's fill in these 2 points. Just use the regular calculation feature on your calculator. Hit log of 0.1. It's -1, right? So we have -1 here. And then log of 0.01 is -2. So let's graph that. 0.01 is basically 0. It's down by -2, -1, 1, 0, and 10, 1. So this graph looks a lot like the exponential function, just kind of in different quadrants and facing a different direction. Okay? So that's your logarithmic function. You can say it has an asymptote at x equals 0, the y-axis. Right? Asymptote's my favorite word. We'll learn another, my favorite math word. We'll do some other of my favorite words this year. Is that even, odd, or neither? Neither. And 1 to 1? Yes, that's the horizontal line. All right, so those are your 8 functions. We learned today 1 to 1. We did even, odd, or neither. And we did 8 parent functions. There's a little bit of practice on the back. Tomorrow we're going to do some practice whiteboards, Canvas, different stuff to review all these and the parent functions. Practice on the back is pretty simple. Determine if these functions are 1 to 1 or not. Decide if they're even, odd, or neither, using whatever characteristics you want to. And then match, there's a blank here. Now I made a mistake. I typed e to the x again. That should be 10 to the x in the blank. Every other worksheet I've corrected. This one I didn't because I was in the middle of copying your packets when I found the mistake, and I didn't want to recopy 70 packets. Okay? So match the functions to the picture. Alright? Easy practice. I would like you to try it. It should not take long. And then that's that.